First of all, I would like to say thanks to KICG for giving me chance to present my research work in front of all you guys. So today I am going to talk about shaping of metal organic framework with activated carbon and silica for CO2 capture. So since this conference is going on, you have been listening a lot about how the CO2 is in fact on our environment and the global warming issue. So I will not discuss more about this. So if we see the CO2 emission from 1750 to 2020, United States and China emits more CO2 as compared to other countries. So the question is how to reduce this CO2 emission. So there are two ways. The first way is by using non-carbon energy sources, and second one is carbon capture and storage. So next thing is how CO2 can be absorbed. So by using absorption by solid, absorption by liquid, and membrane separation. So these are the some methods that we used for CO2 capture. Now which technology is used for CO2 capture? So there are three technologies, that is pre-combustion, oxy-fuel, and post-combustion. So I will move forward. So this is the metal organic framework that we are going to discuss in this research work. So metal organic framework is nothing but the combination of organic linker and metal precursor, that is coordinate framework. We call it as coordinate framework. So metal organic framework nowadays, it has been used in many research like batteries, energy storage purpose, because of its unique properties such as high surface area, specific pore size, as well as pore volume. So the question is how we synthesize these metal organic frameworks. So until now there have been several techniques used for the synthesis of MOFs, such as electrochemical, mechanochemical, sonochemical, solvothermal. Instead of this, there are other methods as well, that is Solgen method. Now, before moving towards my main research, it's necessary to know the goal or objective of this study. So if we see the research that has been done on MOF as well as CO2 capture, there has been several MOFs synthesized, but if we see the cost of that MOF synthesis is very high. Until now, MOF 74 MOF has been developed, and if we see the cost of that MOF for 1 gram, it's around $65 US. So it's very expensive. So researchers until now only focusing on how to develop new MOF and how to enhance its CO2 capacity. But very few research has been done how we can use that MOF for actual application. So I am focusing on this research how we can utilize the MOF for the practical application or industrial application. So for that, I have selected these two MOFs, that is UTC-16 cobalt and UTC-16 zinc. So I specially mentioned that this MOF we developed, novel MOF we developed in our laboratory, and the cost of this MOF synthesis is less than $1 US, that is $0.9 US. And if we see the performance of this MOF, this MOF captures CO2 capacity around 4.7 millimole and has selectivity around 108 for 298 Kelvin and 1 bar. So this is the MOF developed by microwave method, and this MOF also cobalt developed by microwave method. The synthesis of this MOF is cost is around $3 US for 1 gram. So the cost has been calculated based on the sigma price available. So why we selected this MOF? Because of its high CO2 capacity as well as selectivity. Until now, as I said, MOF 74 has a good capacity, but if we see the cost wise, it has having high cost. So we selected some commercially available porous absorbents such as activated carbon and silica. We selected activated carbon for sigma enrich, and we combined this activated carbon and silica with these two MOFs, and we checked how it shows the performance. So with the help of PVB as a binder, we made pallet by using hand palletizer. So as you see here, the AC has high surface area. Once we start adding the percentage of MOF, the surface area slightly decreased up to 30%, but again it increased, but not more than starting material. Also, silica has a higher surface area as compared to parent MOF. So once we start increasing the percentage of MOF, the surface area slightly decreased, but later it on increased. So this is all about surface area and pore volume after addition of MOF. So this is in characterization part, we can see that the polygonal shape of particles, tightly held with activated carbon. So this is the AC UTC16 cobalt 30%, and this is AC UTC16 cobalt 50%. So this is all about SCM image. So this is EDS data, that is purple color represent carbon atom, and this is all about which color represent which atom. So yeah, this is the main result of this study. So as we see here, even though if we make pallets, some MOFs showing good performance for powder, but powder is not good for commercial use. So we made pallet by using this UTC16 cobalt, and if we see, even though we made pallet, it shows good CO2 capacity, that is 4.6 millimole at 98 Kelvin and 1 bar. And when we mix this UTC16 with AC, we observe that it's reach around 3.4 millimole per gram. But if we see the only AC pellets, its performance is very poor, that is 1.8 millimole. And if we see the selectivity, it's less than 20. But after addition of this UTC16 MOF in AC, selectivity also increased. I will show you in next slide. This is the silica pellets, another porous material which is available cheap in market. If we see the CO2 capacity, it's less than 1. But when we increase MOF percentage in silica, the capacity, I mentioned wrong here, so I will correct it later. Its capacity also decreased, but not higher than AC MOF composite. Also, we perform selectivity, that is CO2 absorption capacity at different temperature, and we see that this is a well-known phenomena. When we increase the temperature, CO2 capacity as well as N2 capacity decreased. So similar phenomena observed in this case also. And if we see the selectivity, as I said, the selectivity as 298 Kelvin is reached up to 50. So if we see the AC palette only, the selectivity is less than 20. But if we mix MOF with this, that is for 30%, the selectivity reached 50%. And even if we increase temperature, because of as compared to CO2, N2 capacity is decreased significantly. That's why at high temperature, the selectivity reached around 60 for the cobalt MOF. But if we see the zinc MOF, the selectivity is around 65, and if we increase the temperature, the selectivity is reached more than 70. So this is the good thing that we can use combined MOF with porous material which is available cheap in market. Furthermore, it is necessary to check if we mix the MOF and porous material, but how about its stability? If we mix and if it is not stable, then there is no use. So we also checked how the performance of this MOF under a flue gas, that is as humid gas environment as well as SO2 and O2 gas environment. And interestingly, we observed that the MOF that we developed in our laboratory, that is UTC16, shows a consistent performance. If we see the capacity, it's around 3 millimole, and if we expose to N2, if you see this is a bar of N2 exposure, the capacity is not decreased too much. It means this MOF is consistent, stable under this NOD environment. And if we expose to SO2, this also stable, it's not significantly decreased. But the cobalt MOF is, as compared to zinc MOF, the cobalt MOF after exposed to SO2, slightly, capacity is decreased slightly, but zinc is stable under acid as well as humid gas environment. So this is the FTIR after exposing to NO2 and SO2, and we can see clearly at this 620 wavelength, there is a SO stretching observed. There is a peak around this after exposed to SO2. So to check the concentration of SO2 and NO2, we use the Trager tube, and to measure 15 ppm, we need 10 stroke, and to measure 10 ppm NO2, we need 5 stroke. So the overall conclusion is that we synthesized successfully UTC-16 cobalt and zinc in our laboratory, and our strategy to add MOF into cheap porous material is successfully made. And and the production cost of this MOF as well as composite MOF AC pellets is very reasonable. Thank you for your attention.
네, 답변 감사합니다. 혹시 질문 있으신가요? 영어로 질문을 해야 될 것 같은데 제가 하나 할게요. Can you explain why cobalt and zinc MOF have different absorption capacity? Because they have the same similar pore structures, right?
Different capacity?
Yeah, absorption amount of the bottom, is this the cobalt?
No, this is all about cobalt that we selected a good material.
It has a similar absorption selectivity, okay. And I think the MOF itself has a very high absorption capacity. But what is the reason of the mixing carbon or the silicon with MOF?
Actually, if we see the silica, silica shows poor performance because as compared to activated carbon, silica has a more porous nature. When we mix with binder like PVB, it becomes sticky and it blocks all open metal site as well as open pores. So because of this reason, the capacity is significantly decreased. But if we see the activated carbon is not like silica. The particle size is bigger. So there is no way to block the open metal site as well as pores. So as compared to silica, activated carbon showing better performance when we make composite with MOFs. And as we see, as you ask me, the why zinc is good as compared to cobalt. So according to me, because we are working on that because of our lab limitations. So it should need some simulation work to see how the zinc performance is better than cobalt. But according to my knowledge, I think in UTC-16 zinc there may be possibility of existence of more open metal sites. Maybe because of that reason, it's showing good selectivity.
My question was that the UTSA-15 pellet, the first one, it can be present as a pellet itself, right? In that case, why do you mix with the silicon or carbon with them?
No, yeah, that is as I said earlier presentation, if we use MOF only, it's very expensive.
Okay.
Yeah, so our purpose is to find the middle way. If we use MOF only, performance is good, but very expensive. And if we use cheap material, performance is poor. So that's why we are finding middle way. So that by mixing MOF and porous material.
Okay. Thank you.